more minutes till we get started. So most should be done with the point. Remember, in order to earn education credit, you have to have at least completed more than halfway through the questions. And then in order to get the gain point, you need to finish the whole bell work and get an 80%. If you weren't here last class, you weren't present for the lesson because you were taking a makeup exam or you weren't here, then the bell work should stay open for the next several hours. And when you're done with the lesson today, you could go back and do it. So you're still expected to complete today's bell work. So we're going to go ahead and get started. A couple of things before I get started with the lesson. First, quarter one is done. Like done. We are over with quarter one. We are now in quarter two. So anything including today's homework that was due is all for quarter two. Everything from now on is for quarter two. In quarter two, we'll cover unit 3 and unit 4, which is the second phase of the class. We'll be working with compounds in this phase. And everything you need to know about how to write compounds correctly, what elements form different types of compounds, what are their different properties. You can expect to get a lab next month. I told you the pace is usually about 1 lab a month, so expect to have a lab sometime in November. I don't have the exact date yet, but expect that it's coming. And usually it's after I teach ionic and covalent compounds. So we're probably a couple weeks away from that because we've only done the first lesson. And so remember that also coming up we have a fall break actually in about 3 weeks, not too long from now. You will not have your next exam before fall break. It will definitely be after fall break, but not the day after fall break. I don't believe in giving exams right after a break. So if it's after fall break, it'll probably be either at the end of that week or the beginning of the week after, is right now what I have planned, which gets us about close to progress. So let's go ahead and get started with today's lesson. Today we're going to do Unit 3, Lesson 2, so make sure you're writing down the title in your notes. Remember, if you missed last class, you need to go back, watch the notes, or get the notes from your friend, and you need to have those to show me. The next binder check will be on Unit 3, when Unit 3 is completed on the day of the exam. So today we're doing Unit 3, Lesson 2, and today we're solely talking about ionic compounds. I'm going to do a quick reminder on how ions are formed, but I'm not spending the hour I spent last class going over that. So, Unit 3, Lesson 2, ionic compounds. Today we're going to focus on what type of elements make ionic compounds, a review on how to make ionic compounds from different elements, and then how to name them, which is going to be one of the first major things you'll need to know this unit. There's actually going to be 2 quizzes in Unit 3. One of them is going to be naming compounds, and the other one is going to be drawing Lewis structures, which are electron dot structures for compounds. Those will be both in the month of November. I don't have the exact date yet. I have to work on it on the teacher planning day, but I'll let you know probably next week when your first quiz is. Not saying your first quiz is next week. I'll let you know next week when it is. So Unit 3, let's do ionic compounds. Let's go ahead and get started. You should take out your periodic table that I gave you last class, the one that you write Unit 3 on. Yes. Is that screen sharing? It must have kicked me out. Thank you. I will fix it right now. Because I was screen sharing. Oh. Well, that's unfortunate. But I'm in here. Oh, looks like well, it's not going to kick me off. All right, so last class, I encouraged everyone to either take out their periodic table that had the periodic trends or to get a brand new periodic table that you would just label for Unit 3. And that way you have one periodic table to work on for Unit 3. On this periodic table, I asked everyone to write the ionic charges for the main group elements. The S and P block elements are the main group elements. So the first and foremost thing you are going to have to just straight up memorize. And I did full explanation on why last class, but you gotta memorize this, or else you're in a bad situation for the rest of the school year. So I'm just being honest with you. Every element in group 1, when it forms an ion, it forms a very specific ionic charge. What is it? It's always the same. Positive what? Positive what? Right? Because metals lose all the valence electrons they have. So every element in group 1 loses 1 electron when it forms an ion to be like a clear gas. Every element in group 2 is +2. Every element in group 13 is +3. Then 14 gets a little bit strange. 15 is -3, 16 -2, 17 -1, and then 18, no compounds, no ions. So group 18 would gain 4 little electrons, this is already stable as is. This formulates the foundation of how ionic compounds are formed, so you've got to memorize this information. Maybe it sounds, for those of you who've heard me say this, I've said this now probably like 3 or 4 times. You're going to hear me say it probably 3 or 4 more times because it is that important that you have it memorized. I can't overemphasize how important it is because this leads into not only compound formation, but also chemical reactions. When you complete chemical reactions correctly, it depends on what the charges of the elements in the compounds you're making are, how you make the correct compounds when you mix new elements together. And so it's really, really important moving forward that you just straight up memorize this information. I gave you all the why last class. So if you need to go back and revisit that, I did post the notes yesterday after school. So here's where we're going to start today. A chemical formula. In math, you hear formula, you hear like y equals mx plus b, or you hear some kind of mathematical formula. In chemistry, when we say chemical formula, it's pretty deceiving actually, because a chemical formula is just the representation of a compound that tells how many of each element we have in that compound. So the chemical formula for calcium chloride, for example, is CaCl2. For methane is CH4. For water is H2O. So when you see the word chemical formula in chemistry, what we're really saying is we're just looking for these. We're looking for what elements we have and how many do we have of that element. I'm going to give you some time to write that down. And I brought this up last class, but I feel like it's important to bring it up again. For ionic compounds, when you write a chemical formula, you have to give the simplest whole number ratio. So if you can simplify, you must simplify. Remember, this whole unit's about compounds. So the second definition is, what is a compound? Well, this is when we have 2 or more elements that are combined together. They're connected to each other in a fixed ratio. The way we understand it is they're actually bonded to one another. So this means they're actually very difficult to separate. So I'm giving you some time to write this down and then we'll continue. which of these makes an ionic compound? I was just checking to see if you could figure it out before it was formally defined. So that we're going to define on the next slide. Before I define it, I want to bring up something. You don't have to write this down because we talked about this last class. In the ionic bond, if you'll recall, I showed you an example of sodium that had lost its electron and chlorine that had gained the electron. The actual ionic bond that forms is the attraction between the positively charged sodium and the negatively charged chlorine. That the oppositely charged particles attract to each other, which means that cations would always be attracted to anions. So given that information, can you come up with what type of elements form an ionic compound? Given that amount of information, knowing that cations attract to anions and that compounds require you to have two or more elements that are fused together. What type of elements would we be looking at? What type of elements make positive charges? S block, okay, yeah. What type of elements make positive charges? Metals or non-metals? I'll give you a word bank. Metals, right? Because metals always lose electrons. And what type of elements gain electrons? Non-metals. So if an ionic compound is formed from ionic bonds, which is cations attracted to anions, then what types of elements must there be for you to have an ionic compound? You need two elements. A cation and an anion. A metal and a non-metal. Is there somebody? Oh, okay. Sorry about that. It's okay. So, our definition for ionic compound is then, it is a compound composed of cations and anions. An ionic compound is a compound composed of cations and anions. And you'll notice what I put in here. It is typically a metal.
Please pardon this interruption. The students who need to make up the PSAT need to report to 249. Melanie Carballo Lugo, George Espinosa, Hayden Ava, Ryan Matamatos, and David Montes de Oca. Those students only, those 5 students, report to 249. Sabrina Ford, you can meet me in 249, but you will not be testing today. Thank you.
So, ionic compound is formed of ions. A positive ion and a negative ion. All right, I'm moving forward in about 20 seconds. I'm just giving you a heads up. All right, continuing now. So, does anybody not have this paper? I passed it out last class. If you don't have a copy of this paper, raise your hand. The crisscross method of creating ionic compounds. You need a copy of it? You do have it right there. No worries. So last class, at the end of class, we had went over how to create ionic compounds by looking at the elements involved in creating a compound. And so that's how the bell work is, and that's how the homework was, is that you would be given two elements to combine to make the ionic compound. And so there are two steps that you need to remember in how to make ionic compounds. Step one, you have to find out what the ions are. How will you find out what the ions are? Looking at the charges and the groups and the periodic table for most elements, this will work. And step two is to cross the charge of the ions. Step two, you're going to take the charge of one of the ions and you're going to negative the amount of the other. This will always balance out the charges. Remember that an ionic compound overall has to have a charge of? An ionic compound overall has to have a charge of? So the charges must always balance out. And when you take the charges and you cross them and they become the amount of the other element, this will always balance out the charges. You'll have a net charge of 0. And so a couple of things that I told the class to remember last class is that when you cross the charges to become amounts, that amounts must be, what I said? Positive. So that's the one thing. You cannot have a -2 amount of an element. And the other thing is that if you can simplify, then you must simplify. If you can, you must simplify. Because the idea of an ionic compound is it's the simplest whole number ratio. The simplest amount that you need to make that electron transfer happen, where one element will lose the same amount of electrons as the other element will gain. So to make the simplest transfer, that's the idea. All right, so I just wanted to re-go over that because I do know that there were about 5 students missing last class when I was teaching this or testing at the same time. Continue. Predict the chemical formula when the following sets of ions are combined to make a neutral compound. So go ahead and write this down in your notes. This is review from last class. How do we do this? So review from last class, but write it in your notes, because this is where we're starting the day today. I've got Mg2 plus and P3 minus. Could I have made you get those ions yourself? Yes. So I've actually already done step 1 for you here, and you just have to do step 2. Check it first to see if you've got the idea, and then I'm going to go over it in a minute. Okay, so for the first one, Mg2 plus and P. First step's already been done. So all you have to do is take the charge of one, make it the amount of the other. So the answer here would be Mg3, P2. And we would put -3 there. It has to be positive at the the bottom because these are physical amounts, and amounts cannot be negative. The idea is you're balancing the charges by fixing the amounts. Mg3. Na plus and C4 minus. Na plus 1 and C minus 4.
So C is 1 and
Yeah. And then last one, PB4 plus O2 minus. Do you have to crisscross to figure it out? I have one question. You could say, well, I know that this blood is given 4 electrons away, each oxygen has 2, so with understanding of that, you could draw the conclusion that you need 2 oxygens for 1 blood, because 4 and 4 would be the equal transfer. However, if you blindly follow, like I said last class, crisscross, that's the method you're going to use, just to try to make sure you get as much answers correct as possible, you would come up with this. You would come up with PB 2O4. But this is actually not correct. If you can simplify, you must simplify for ionic compounds because we're showing the simplest transfer of electrons, the lowest amount we need to make it work to get a neutral compound. Divide both by 2 and we get PbO2. Do I need to write the 1 here? No, but we kind of be like for good measure. It won't be shown to you on a quizzes or like practice questions, but you could write it yourself if you need to. And so you've got PbO2. This is what we learned last class that can get you through the homework from last class for those of you who were testing. And if the charges aren't given, you get them from the periodic table. So now we're going to move on to what's new. What's new is how do we name? So if I give you a compound, how do you name the compound? Before I teach you how to name the compound, I have to teach you how to name individual cations and individual anions before we bring it together to make the compound. So you should write down pretty much everything that's here is important. How to name cations and how to name anions. This is going to lead us to how we write the names properly of ionic compounds. Luckily for you, the names of the elements you can find on the periodic table because the Cambridge periodic table gives you both the names and the symbols. But for naming anions, you have a little bit more work to do. So go ahead and write this down and we'll go over it shortly.
So I paused to give you some time to write down both how to name cations and how to name anions.
So the naming of elements is based on if they're a cation or in an ion. For cations, it's actually very simple to write the name of the cation. You find the name of the element on the periodic table and you add the word ion. So for example, if you see SR2+, that would be strontium ion. For anions, you actually have a little bit more work. For anions, after the first syllable, you drop the end of the name and you change the ending of the name to IDE. You might have seen this before. You might have seen it passing the word oxide or sulfide or fluoride or bromide. That means with the IDE ending that this is actually not the element by itself, it's actually gained electrons. And so that's what the IDE ending indicates. And so now we're going to learn how to write cations and anions individually, and then we'll put them together to form compounds. I'm leaving this up for about 20 more seconds. For anybody who needs to take a picture, you didn't quite finish, you were outside of the room for a moment, make sure to do so now before I move forward. Good? So, go ahead, here's the first set of examples. Name the following. We have 3 examples here. Name each of these cations. So they're official cations. What is the name of Ba2+? What is the name of Al3+? What is the name of Rb+? Naming cations. Ba2+. What do we have? Find the element on the periodic table. What is it? And so you just say barium ion, Bn. Direction set. Right, the name from the periodic table, you add the word ion. Yes, it's that simple. I actually added these slides to break it up because in the past I don't think students realized how simple it was. For Al3+, you find the element aluminium, and then you just write the word ion. And then Rb+ would be rubidium, and then ion. So cations, metals that are fixed charge, which are the only ones we've discussed so far, are very simple to name. In a little while, we're going to look at transition metals and for transition metals in addition to it. But for now, this is where we're at. Well, let's take a look at anions. Cations. I'm going to leave this about 20 more seconds. Anions. So remember that it said for anions, you write the first syllable from the element's name of the periodic table, then you drop the rest of the word and you change the ending to I-D-E. But you'll also notice I said that there were some. What do I mean by that? I mean there are some that you actually drop the second syllable. And so I'm going to list those out for you after we do these 3 because these are all ones that doesn't happen with. So using the directions you've been told, what would the name of S2- be? the sulfide, because remember, it's sulfur. You keep the first syllable, you drop the last. Drop the last syllable, change the ending to I-D-E, and then because it is just the 2 minus charge, we put the word ion following it. We say it's the sulfide ion. O2 minus. So this was the element oxygen. We dropped everything after the first syllable, so ox, and then instead of writing oxygen, we write ox-I. So it's the oxide ion. And then N for nitrogen. Notice where we're dropping. It's after the last syllable, after the last consonant of the first syllable. So nitra, nitride. Nitride ion. Now, I am going to list the exceptions here so that you have them, so that when you see questions, you're not confused. The exceptions are arsenic. Arsenic becomes arsenide. Selenium. Selenium actually becomes selenide. So you'll see in these, you're actually dropping just the last syllable. And telluride. Tellurium. Telluride. And the last one is silicon. Is silicide. Those are the exceptions, meaning that for these specific elements, you don't drop after the first syllable, you actually drop after the second syllable. They're not used very often, but they do show up in questions, so I did want to bring up what the exceptions are because you will see it in your homework or in a quizzes, and you can go back and review over it. But other than those exceptions, the idea is that it's the first syllable at the last consonant, that's where you drop off. And yes, I know that sounds like English, but this is actually chemical communication is what we're studying when we're studying how to name properly. How do you scientifically represent what you're talking about? So that everyone understands the same language. So I'll be teaching chemical language some over the next week and a half.
All right, I'm giving you a little bit more time and then we're going to continue.
So name ionic compounds. Ionic compounds are made of a cation and an anion. And so you're going to have to name both the cation and the anion in order to come up with the name of the ionic compound. And so just to be clear, this is what you will do. How to put the name of an ionic compound together. So I wrote some instructions here. You're going to write the cation name, then you're going to write the anion name as two separate words. For each of your ions, you're going to drop the word ion when you put it into the compound, which means, in a very, very simple one, NaCl. You know this is made of sodium ion, and this is made of chloride ions, but it doesn't make sense to say sodium ion, chloride ion. You drop the word ion, and it's just sodium chloride. So just to give you an example of what I mean by these instructions. So you name your cation, you name your anion, but you don't include the word ion because the charges have been balanced out in the overall ion compound. So this is sodium chloride, which is table salt, which we need to split, and also makes food tasty. Have you ever had unsalted fries? They're awful. Not much flavor. They take on the flavor of whatever you add to the potato. Yes. Yeah. I'm moving forward in about 20 seconds just to give you that heads up. All right, let's take a look at some examples. So these are examples. Name each of the following. Go ahead and write them down. You want to have them for your notes. If you think you've got a good grasp on what to do, go ahead and start solving them, and then just check to see if you've got the right answer as I go over them. So you've got CaBr2, BaO, Na2TE, and CSF. Before you even start naming them, how do we know that, first of all, these are compounds, and second of all, these are all ionic compounds? Like, you're just being told on the side, it says naming ionic compounds, but how do you know these are all compounds? And how do you know they are ionic compounds? Because where this will get more difficult is we're going to learn another type of compound, which has a different type of naming, and then you're going to have to differentiate between the two. Not today, but that's where we're going to go. Go ahead. So how do we know? So compound equal 2 or more elements. And how do we know we have 2 or more elements in CaBr2?
Because there are two
Uppercase letters. Every uppercase letter starts a new element. So that tells me we have calcium and we have bromine. So here it's Ca is one element and O is the other. And A is one element, Pe is the other. So a compound is 2 or more elements. I know it's a compound. Now how do I know it's ionic? What is similar about all of these that makes them all ionic compounds? They are all forms of metals and non-metals. You have to have both a metal and a non-metal. If you have 2 metals, you don't have an ionic compound. If you have 2 non-metals, you don't have an ionic compound. You need to have a metal and a non-metal. One has to give away electrons and the other one has to receive. That's the idea. So now that I've said that, that's how we know this is what we have to name. Then we just follow the strategy. First element is Ca. Is that a cation or an anion? Positive charge or negative charge? Positive. So that means you just write the name from the periodic table. So it's Ca is calcium. Second element is Br. Is that a cation or an anion? Anion. So to name an anion, you change the ending of the name to, so it's calcium bromine, correct. I'm just going to underline this because that's the change I made. And we drop the word ion for both when we put the compound. So when I name just the anion and cation, I write the word ion, but when I'm writing them together, I drop the word ion. All right, BaO. Ba. Ba, look at it. It's barium. Barium.
It's barium.
Yeah, no, just right.
And then,
Barium oxide.
Well, what do you do with the anion? You have to cut off after the first syllable and you change the ending to IDE, so it would be
Oxide.
oxide. You'll see there's a pattern. Next one. First element is sodium. The first element, you'll notice we're never changing the name up. We just write the name from the periodic table. I'm going to bring this up like why? After. And TE? Tellurium. Remember that was an exception. Look at what you wrote. What does that change to? Telluride. And so you'll just see me. You don't have to do this, but I'm just underlining this to say this is the change. That was me. And then CSF. First element is. And second element is fluorine, but we don't write fluorine when it's gaining an electron. We write
Fluoride.
fluoride. Very good. Fluoride. I had a professor. I just paused for a second. I had a professor. And some of you might accidentally make this mistake. However, you've got a periodic table so that has all the names, so you shouldn't. When a lot of students see fluorine, they accidentally write this. But what's that? Flour. Like, baking flour. And so I had a professor that was his trigger. If a student ever wrote fluoride, he was like, no.
I'll just forget the U.
Just forget the U.
Yeah.
Flowride. There was a rapper named Flowrida. But anyways, that's why I paused for a second. I was like, it's UO, not OU. It's a very easy
I did it.
You did it? It's a very easy, but it's not my pet peeve. But it's not, I don't think it's Cambridge's pet peeve either. But I had a professor who was their personal pet peeve that they could not stand if somebody wrote fluorine with the OU instead of the UO. Like it's supposed to be with the UO. Anyways, so that's it. I want to bring up, notice there's a pattern, first of all. The first element, you don't change anything. The second element, you always change the ending to IDE.
IDE.
In ionic compounds, always the cation is written first and the anion is written last. And this is how, and I know some of you did it differently in your homework. I saw for the few of you that showed it to me before you turned it in. And I'm not gonna knock you for it on the homework because I didn't explicitly define it yet. But from now on, you have to know whenever you see an ionic compound, you're actually gonna write the metal first and the non-metal second. That is the official order. It is cation plus anion.
Any questions?
Yes, all the questions are written in order of cation plus anion.
Yeah, I
Right.
know for certain for some I did.
And I wrote it here. I wrote it here. Write the cation name plus the anion name. It is in that specific order, and that's how it will always be presented to you. All right, well, some of you may be thinking to yourself, wow, this sounds really easy. Here's sus. Suspicious.
It gets harder.
I told you last class, but I'm going to repeat now. This unit is a traditional unit of study for this class, which means that the first lesson was the easiest. And as we add more information, it will get more difficult through the unit. So we have left out a lot of elements. We've only talked about, elements here and elements that are here, right? But there are compounds with iron. There's a lot of them. There are compounds with copper. There's a lot of them. So we are now going to talk about the transition metals. Go ahead and write down where transition metals now enter the conversation. So how do we find the charges for transition metals and how do we name transition metals? And it's really, how do we name something that we don't know the charge of just by looking at it on the periodic table? Because I told you last class and also last unit that we only can get the charge for group 1, group 2, and then group 13 through 17. Well, what about everything else? What about everything else? Well, first of all, the radioactive elements you're really not going to see compounds with because they decomp before they form compounds. But these elements you will see compounds with: manganese, chromium, cobalt, iron. You will see a lot of nickel. You'll see a lot of compounds with those elements. And so we have to discuss, well, how do we name those compounds and how do we get the ion for the metals in those compounds? Like, how do we know what they are? When every single transition metal has 2 valence electrons. And remember I told you that transition metals are always more complicated. Whenever we look at transition metals, things get more complicated. But what about transition metals? Ready? All right, so there's good news and bad news. I'm just gonna stay that way. You want which one?
Bad news.
The bad news, the bad news.
Yeah.
The bad news is you can't figure out the charge.
So they give it to you.
Right, so it has to be given to you.
Um,
So that's bad news. So the bad news is many of the transition metals make cations with different ionic charges. What do we mean by that? Iron could be +2 or +3. Copper could be +1 or +2. These are some examples. You may want to write them down because these are the most commonly tested. And some of them are transition metals and some of them are actually post-transition metals. Yeah. So you may want to write down that these are examples of metals that don't have a fixed charge. Examples of metals that don't have a fixed charge, meaning they don't always have the same charge. You may have seen this in the homework with the Roman numeral, and you may have seen this in the bell work. I left, I think, at least one in the bell work of those that's there. So chromium, manganese, FeCO, Cu, Hg, Sn, and Pb. I would write those down as examples of metals that form more than one potential ion. Sn, Pb, Hg. I'm going to give you a way to look at your periodic table and know shortly, but it's a good idea to have the most common ones written down. So the bad news, well, we don't know what their charge is because it could be different things. The good news, well, you will have to be told it in some way. And so that's where the Roman numerals come in. If you see a Roman numeral, that means that you are being communicated how many electrons that specific metal has lost. Which means if you see a Roman numeral, this means you definitely have a metal that can form more than one charge. It's being given to you for a reason, the Roman numeral. Because they're telling you which version this is. So I'm leaving this up for a little bit and then we'll get to, well, how do we account for this when we name compounds with these metals that have different ionic charges? Once again, you'll want your periodic table out because we're going to mark it a little bit. Theory words in chemistry are some. That means that this is not everything, or many. Many means not all, right? Which means both of these words mean there are exceptions to what's being said here. And so I'm going to make it a little bit spooky science for real. Actually, I see you all on Halloween.
Yeah.
That's good. See you on Halloween.
You want to see me? We're going to do like
Jump scare. Chemistry jump scare.
you don't want to see me on
I have not exact. I only have one thing that I know that I've planned for Halloween so far, but let me think on teacher planning day.
Oh, you should do like
You know how much work that was?
but it's super fun.
I know, but Miss Fleet spent $150 and about 20 hours of prep to make that happen. So you're welcome. For those of you who went.
You should have done 25 hours.
Oh, okay.
No, you should.
All right. So, what do we do? You've all actually gotten a clue. I gave you a clue last class. in your homework, whenever you have, and there's a mistake here, this should be +1. It's an image, so I can't fix it. I have to write over it. Like, I can't fix an image unless I guess I Photoshop. I don't know. Anyways, this should be 1+. And other than that, what you should note here is for the different versions of the element, you're going to write Roman numerals to tell their different charges. So if you have copper with a +1 charge, you call it copper 1 ion, where 1 is a Roman numeral. So if you have copper +2, this is copper 2 ion. If you have lead +2, this is lead 2. And if you have a lead +4, this is lead 4. You actually need to memorize a specific set of Roman numerals for this class. When I mentioned this last class, I think some people freaked out when I said the words Roman numerals. The good news is it's 1 through 7. You only need to memorize the Roman numerals 1 through 7 in this class. Meaning if you see I, that always stands for +1. I is +2. I is +3. IV is +4. V is +5. VI is +7, and VII. Actually, there's an off chance you could get +6 and +7. Memorize Roman numerals. 1 through 7. Roman numerals are exclusively used for metals, not non-metals. I'm going to say that again. Roman numerals are exclusively used for metals, not non-metals. This is a question I've gotten a lot in the past. That's why I'm telling you explicitly. We only use it for metals when there's a possibility that that metal could have a different charge than the one that is there. So you'll notice there's a stock name. We only use stock names in modern science. And there's a classical name. The classical name is like pre-1950s. So ancient history. The classical name like classical music. So the old name for copper was cupris. Copper 1 used to be called cupris. Copper 2 used to be called cupric. Lead 2 used to be called plumbus. Lead 4 used to be called plumbic. Take a look at those classical names and look at the chemical symbols.
The symbols are based on the ancient names.
For those chemical symbols that don't match our current elements, it means that they're based on the classical name. So like cupris is how we got Cu for copper, which on its outset didn't make any sense, but hopefully it makes at least a little sense now how that came about. And plumbus, I love that. Plumbus, Pb, lead. But it's not Ld or something. Pb, lead, because of its classical name. So that means there's other elements here. Look at silver, Ag. That means its classical name has to have had an A and a G, argentum. I believe this is classical. And so it's the old names. That's why, and some of them they just stuck, I guess, with time. So that's why we still use their old symbols. They have not, the IUPAC, which is the International Union of Pure and Applied Chemistry, have not changed the chemical symbols. That doesn't mean they can't. Maybe your children, grandchildren will study a periodic table where they've changed chemical symbols to match the.
It's been so long.
Exactly.
Yeah, a bunch of people.
So people just stuck with it.
If they changed them, a bunch of people would probably react like when they made Pluto not a planet.
We
They've all
tried
been-
to do the metric system in the 1970s. Failed not. Like to change everything to the metric system in America. It failed in the 1970s, and they never tried again. Even though metric system, when we go to measurements later on in the year, we get to all of the math part of the class. If we started by learning metric system, our lives would be so much easier. All right, so what does this mean? Use a Roman numeral if you don't know the charge of the metal. That's what this means. And so that's what this is going to say. So a few transition metals have only one ionic charge, and you should write this down. If you have a transition metal that has a fixed charge, it does not get a Roman numeral. So Roman numerals are used only for metals that have more than one possible charge. And what we mean by that is there's more than one possible configuration that can make that metal stable in a compound. Good news and bad news here as well. The exceptions here have to be memorized.
What's the good news?
There's an easy way to memorize them. So we're going to head to a periodic table right after here. So I'm giving you some time because there's definitely a decent amount of information here. And then we're going to go to a periodic table to go over, well, what does this all mean? So have your periodic table that you wrote your charges on out. The first thing we're adding to initial naming was just naming the cation from the element name in the periodic table and naming the anion by dropping after the last syllable and changing the name ending to IDE. Now we have stated that if we have an element that could have more than one charge, we also have to use a Roman numeral to say what its charge is in its name. Positive, always positive. Only for the metals does this happen. It never happens for the non-metals. Non-metals have a fixed charge. All the non-metals have fixed charge. So I'm leaving this up for about 20 more seconds. We're going to then head to a periodic table. So be ready to write on a periodic table. So back to our periodic table. All the way where we started. All the way back. Here. So remember we filled in the charges, right? Write those three exceptions. What was silver? +1. What's cadmium? What's zinc? What group is silver in? Silver's in 11, and it has a +1. Cadmium and zinc are in 12, and it has a +2. Take the 1 away, and you've got their fixed charges. Silver 1, zinc and cadmium 2. That's an easy way to remember. Those specific transition metals have fixed charges. All right. and add the +3 to aluminum, because we know that that has a fixed charge. Add the +3 to aluminum for yourself. Any metal that is in the transition metal section, and I'm just gonna go, all right, where are our metals? We're like this, right? So any metal that is in this section, notice I'm making a big box, except for those three, can have variable charges. So that means most transition metals and post-transition metals can have variable charges. What does that mean? That it could be more than one thing. And if it can be more than one thing, then every single one of those elements has to have a Roman numeral in its name. Yes. Yes, I can give you a new one. I printed out like 100 the other day because I figured as we go through the lessons, you may find you need another one. So if anybody does need another periodic table to write on, just let me know. I have more. So if I have a compound with zirconium, would I have to use a Roman numeral, yes or no? Yes. If I have a compound with manganese, would I have to use a Roman numeral, yes or no? For the charge, manganese.
Yes.
Manganese. Okay, now if I have magnesium, would I have to use a Roman numeral? No. So we only use Roman numerals to communicate charges if we don't know what the charges are based on their position of the periodic table. That's the idea. Kind of make sense?
Yeah.
All right. After I've given you some time to finish writing down what's here, we're going to take a look at some more examples so we can get the idea of what's going on. Yes. Yes. So fixed charge, meaning the charge is always the same. No Roman numerals. Variable charge means Roman numeral. So another way of saying this for yourself, fixed charge, no Roman numeral. Variable charge, just to be clear, Roman numeral. And are you going to be expected to look at compounds and know if you use a Roman numeral or not? So if you have a metal with a fixed charge, you do not use a Roman numeral. In all the examples that I initially showed you with naming, I was very careful to choose only metals that had fixed charges. You should be writing this on your periodic table, so you have to go back to when you're looking at practice questions.
And next class is bell work.
Oh yeah, next class is Halloween, isn't it? For this class,
Right? I see this class next on the 31st.
so next class, spell work. You have a 3-day weekend, remember? 3-day weekend. And homecoming. But then you get a 3-day weekend. I think that it was done that way on purpose. Let's put homecoming tonight so that you get the 3-day weekend after. And not school. Giving a little bit more time. I'm giving you a 20-second heads up that I am going to move forward. If you need me to go back here after we do the examples, I can. But we need to work through examples before we finish for the day. I do want to take the opportunity while I'm waiting to share with you that the homework today is digital. It is a science geek homework, which means you have to get the 80%. You take the screenshot, you upload it, and just do it by Monday night is when it's going to be due. So digital homeworks are always due the night before the next class. Either way is fine. You can submit it in person next class or online. just if you submit a paper homework online, I'm gonna say this for everyone, make sure you write a private comment to me. Like if you submit a paper homework online, I prefer you do it on paper. It's much easier to grade that way. But if you put it online, just make a comment so I know to go back to look for it when I'm grading. So I'm not perfect and I can accidentally put in a 0. So make sure that if you do it online and not on paper, that you just let me know. All right, we're good here? All right, let's get to examples. First, so we're gonna have 2 slides with sets of examples and then we're done. I think. Yeah, that's it. So we've got 2 slides with sets of examples and then we're done, which means you should have opportunity to work on the homework today, actually. There's a chance you can finish it before you leave, I bet. And then you don't have homework this weekend. But let's go through what we need to do first and make sure we have full understanding. The first set of questions, write them down in your notes so you have them. You're gonna want these to reflect back on when you do your next spell work as well. Write the chemical formula for the following named compounds. Iron 2 bromide is the first one. We'll go through each one. Okay, so I'm going to start solving the first one. If you're given the name and you are being asked to do the chemical formula, first of all, what's the chemical formula? That's the first definition like we had today. What is that? Which is what? A chemical formula tells us how many of each element are in the stable compound, right?
Yep.
And now I have officially told you that the way that it's written is the order of the elements, right? You have to write iron first, and you have to write whatever bromide is, and just find what element that is second. All right, so that's the first thing. Well, what would be the steps then? Wouldn't they be the steps from here? So your paper from last class where it talks about the crisscross method, we're going to use this to help us come up with the formulas. So step 1 would be for each element, you find the ions. What's the ionic charge for iron 2? Iron Roman numeral 2. He plus 2. So I want you to note for yourself, remember, II stands for plus 2, and it must be for the metal only. You cannot use Roman numerals for non-metals. You can only use them for the metals. Yes?
Yep.
So Fe plus 2. All right. What's bromide? What element was that? You dropped the IDE. Brome. Is there any bromes on the periodic table? There's only one, by the way. You'll be able to figure it out. It's bromine. So you would write the chemical symbol for bromine, which is Br. So far, so good? Oh, you can't only give the symbol, you also have to give the... If I want the chemical formula, I need to get the charge. Well, what's the charge of bromine? Do you have a choice? Or is it always the same thing? This is what we need our periodic table for, right? And we need to memorize these group charges. The charge of bromine is always... Right? Maybe you're starting to see why I said so many times you need to figure out PR is minus 1. Yes? So far, so good?
Yep.
Okay. That was step 1 to make the formula. What's step 2 always?
Now we crisscross.
to make the neutral compound. And so we crisscross, change negatives to positives because amounts must be positive. And so you get Fe1. You have to write a 1,
No, it's not.
but you can if you want, it's optional. And then Br, how many? And that's not optional. You have to know that it's 2 bromines for 1 iron. You okay with this? Yeah, first example. Potassium chloride. Potassium chloride. We actually lit this on fire in our last lab. Just FYI, we did. It gave us a pinkish purple flavor. Is the blend color? Some of you saw like a peach, but it was supposed to be a pinkish purple flavor. The way I memorized it is PP, potassium pink, potassium purple. PP, like the letters at the beginning. Potassium chloride. What's the formula for this? What's the first step? Okay. Oh no, they didn't give me a Roman numeral. Is this a problem?
No, it
No,
means
it
better.
means we know. It means we know what it is. If they don't give us the Roman numeral, what's the charge of potassium? Or at least we know it with a periodic table.
1.
And then chlorine.
This one, negative 1.
So plus 1 minus 1, those just automatically cancel. Do you agree? To make a neutral. This is KCl. Remember that lowercase l and uppercase I look the same as each other. These are all compounds that have 2 elements. So if you see what looks like carbon iodine, it's not carbon iodine, it's chlorine. This is potassium chloride. That's an important note. This is chlorine. The lowercase l looks like uppercase I. Be careful with that because it's going to come up over and over again throughout the class. Whenever you see what looks like it's carbon iodine, it's not. It's chlorine. Chlorine is a very common element to use. All right, lead 4 nitride. Or lead IV nitride. First step, PB. Flumbic. Okay, PB,
And then it's 4.
what's the charge?
4.
Plus 4 or minus 4.
Plus.
Would you ever give a metal a negative charge?
No.
No, you would not. Right. The metals would not. Plus 4. All right, the other element?
And
N.
negative
3. Oh, 3 and 4, that's gross. We can just do crisscross to solve what's going to balance out the charges, right? So, if I didn't teach you that, you would have drawn the electron dot structures and transferred electrons over until all the leads gave over 4 and all the nitrogens accepted 3 until they balanced. Which would have been annoying, which is why we don't do that. I only do it to illustrate to show you how it happens, but this is what we use to actually make the formula. So it's PB, 3, and 4. Yes?
Yes.
Alrighty. Copper 1 oxide. Copper 1 oxide. Cu. What's the charge?
1.
Plus 1. Oxide.
Then O.
What is the charge? -2. Now crisscross. Make the charge of 1 the amount of the other opposing element. You get Cu2. Oh, you have to write the 1?
No.
No.
No, but you can. If you want. Cu2O or Cu2O1 is correct here. Writing the chemical formula when given the name is actually the easier thing to do here because you are literally, if it's a transition metal, being told the charge. The harder part is the last slide because you have to tell the charge if you're given the formula and you're asked to write the name. So we're going to do the last set of examples. I'm leaving this up for about 20 more seconds. Then we'll do the last set of examples. All right, last set. Write this down. You're going to want to have these to reflect on. So now, I'm giving you the chemical formula decisions to make. And whenever you have a decision to make, it gets more complicated because you have to make a choice. And there's a right choice and a wrong choice. So last set of examples. Given the chemical formula, write the name of each of the following. So remember, it's always the cation plus the anion. But now you've got a choice with the cation. Do you use a Roman numeral or not? So fixed charge means no, right? And variable charge means yes to Roman numerals. So you've got a choice. The choice is Roman numerals, yes or no. You may want to write that down for yourself because you have to make a choice now when making the name. And the choice is in the cation. If you have a metal that has a fixed charge, what do we mean by fixed charge?
That we know. Then we
We
don't
know
need
it's
our own
charged for sure. There's no choice. For example, sodium, there is no choice. It is +1. It's +1 every time. So you would not use a Roman numeral for that because why would you communicate that when it's known that it's +1? You only use a Roman numeral to communicate when you don't have the charge. Otherwise. So we're going to start the first example shortly. In about 20 more seconds before I go over, and we'll go over each of these. And the homework should have auto posted. I do set it up to auto post, so as soon as you're ready, you can start working on the problem sets. Definitely, you could get at least 1 out of 2 of them done, and you might get both of them done by the end of class. They're pretty quick. I did not design to give you long homework this week. CaO. What's the first element here?
calcium.
Calcium. So you can write that down, right? So you know it's calcium. The decision. Do you give calcium a Roman numeral or no?
No.
So you would say no to Roman numeral. Why?
Because it's a fixed charge.
We know calcium's +2, right? So based on calcium's position on the periodic table, that we know that every element in group 2 is +2, there's no reason to communicate a Roman numeral. So we just write calcium. And so the anion you don't do anything new with. So what would the name of oxygen be in an ionic compound?
Oxide.
Oxide. Calcium oxide. COI. First element is cobalt.
Oh,
Decision time. Your decision is Roman numeral or no Roman numeral. So we need to go find cobalt on our periodic table, right? Go find it.
I.
It is right here. Do we know the charge of cobalt? No. So we have to use a Roman numeral. But how do we know what the Roman numeral will be? So
Because the
this
I
is
has
where, savvy. You know the crisscross method. You know that the amount of one element is the charge of the other, right? So we do what we call a reverse crisscross, right? The amount of iodine here has to be the charge of cobalt. Cobalt has a +3 charge. You need a Roman numeral. You get it from the formula that's given to you. Are we okay with this idea? So with +3, what would we write?
3 sticks.
3 I.
I for 3 sticks. 3 tally marks is what it looks like. Cobalt 3. And then the end of the name? Iodide.
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 Iodine?
It is iodide. You always end at a consonant. Consonant. So it's iodide. Sounds weird. But that's what it is. Cobalt 3 iodide. Alright, what about the next one?
Yeah.
What do you say? Ni.
Nick.
Do I know the charge of Ni based
Nope.
on its place in the periodic table? Unfortunately not.
So you know.
So I do know it from the formula. So because I don't know it from the periodic table, I'm gonna have to use a Roman numeral, right? That's the decision that you have to make. And then to figure out what that Roman numeral is, we can do what's called the reverse crisscross, which means take the amount of chlorine and make it the charge of nickel. So this is gonna be nickel has what charge?
Plus
Plus 4.
4. So it's gonna be IV.
Nickel, IV, and then Cl is, it's Cl, not Ci.
Fluoride.
It's only 2 elements, so it's Cl. It's chloride,
Fluoride.
nickel 4 chloride. Huh. Two more examples. I have these written on purpose. The next one's a trap. You may want to write next to it. It's a trap. Like Star Wars. It's a trap. It's a trap. Admiral Akbar. It's a trap. Can you figure out what the trap is? I'm giving you the heads up that it's a trap. Can you figure out what the issue is? First of all, do we use a Roman numeral?
Yes.
Because of where iron's at. So we know it's a Roman numeral. So that's not the trap.
We can't crisscross.
It's the
reverse
name.
You can't
the other
crisscross.
Wait, but it's 1. So maybe.
Is it though? Take a look at it closely.
Big 3.
Phosphorus is -3. There's one of each of them. Right? This is 1, 1. What's iron supposed to be? Nope.
Positive.
+3. Think about it. Let's write it a little bit larger. Fe1P1. There's one of each of these, which may mean that it was simplified. So the trap here is if you're given a simplified ionic compound, you have to figure out what the charges are. So this is going to be more complicated. So you have to check to see, well, what's the charge of that nonmetal? What is it? -3. Which means in order for this to be balanced, phosphorus had to gain 3 electrons, iron has to give away. Iron has a +3 charge in order for this to balance out to be 0, and it has to balance out to be 0. All ionic compounds have to balance to 0. Which means that the Roman numeral for iron is actually 3 I's. Iron 3 phosphide. So when could this trick arise? Why did this trap happen?
Because they want to always simplify.
And when could that happen?
When the two things can be divided.
So you should always check your nonmetal. If the nonmetal is not from group 17, this can happen. Check its charge. Why doesn't it matter for group 17? Group 17 always has a -1 charge, so it will always be the most simplified version. Which is why you see most compounds you're given have like something from group 17 because that's the easiest scenario. But once oxygen or sulfur or any of those other nonmetals from group 16 or 15 enter the picture, then you may get this trap. So I'm just warning you, this can happen. It doesn't always happen, but it can. Last one, AgI. Minor trap.
Silver and it's gonna
Minor trap. Not as big of a trap as B. Silver. Roman numeral or not, is that decision.
Yep.
Not a Roman numeral. Why not? There shouldn't be a Roman numeral here. Go back to what you wrote on your periodic table. Silver is what we call an exception. Silver always has a plus one charge. If something always has the same charge, we do not write a numeral. This is silver. No Roman numeral. Iodine. And with that, we are done with naming ionic compounds. There's only one part I've left out intentionally until later in this unit, and it's called polyatomic ions. That is the most complicated part, but it is not a discussion for today.